matter, energy, and light. History of environmental engineering. From the beginning of civilization, environmental engineers provided clean water and managed waste, as it was necessary whenever people congregated in organized settlements. The so-called engineers of antiquity were the builders of wells and aqueducts. During mid-1700s, the term civil engineering was born, as engineers who built facilities for the civilian population. With the arrival of industrialization, unsanitary conditions in the cities were unbelievably great due to the lack of water and waste management. In the late 19th century, the major objective was to eliminate the waterborne disease, and public health became a primary concern of the civil engineers, as they were entrusted with providing water supplies to the population centers. Environment derives from the French word environner, which means to encircle or to surround. Environmental science is a highly interdisciplinary that integrates natural sciences, social sciences, and humanities in a broad holistic study of the world around us. Environmental science is the study of the effects of natural and unnatural processes and of interactions of the physical components of the planet on the environment. With this, we are able to learn about the problems we have created with the environment and take the responsibility of our actions. Environmental engineering is a branch of engineering that aims to improve the quality of environment and promotes protection of people from adverse environmental effects like pollution. Environmental engineering combines natural sciences like chemistry and biology with engineering principles to come up with the solution to the environmental problems. The three main things of environmental science and engineering. Number 1. Protecting people from the environment. Number 2. Protecting the environment from people. And number 3. Improving the overall quality of the world around us.
Ecology isn't just about species-rich forests, pristine wilderness, or scenic vistas. For instance, have you ever found cockroach living under your bed, mold growing in your shower, or even fungus creeping in between your toes? If so, then you've seen equally valid example of ecology in action. A compound found mainly in living things is known as organic compound. Organic compounds make up the cells and other structures in organisms and carry out life processes. Carbon is the main element in organic compound. So carbon is essential to the life on Earth. Without carbon, the life as we know it could not exist.
On Earth, materials exist in one of the three main states of matter: solid, liquid, or gas. Materials can change between these states. When state change occurs, a substance's properties will also change. However, if the state change is reversed, the substance will recover the properties it had to begin with. Matter can transition between the three states when heated or cooled. When a material is heated, it absorbs heat energy. This additional energy can cause attractive forces between molecules to break. This leads to rearrangement of the particles because the attractive forces no longer hold them together as tightly. The same happens when a liquid is heated. The attractive forces between the molecules break, leading them to become more widely dispersed and a gas to form. Both are when a substance transforms from a liquid to a gas. Think of a boiling pan of water, all of the water bubbles. This is because all of the particles have enough energy to become gaseous. But water standing in a pan that is not being heated by anything other than the environment can also turn into a gas. This is evaporation. Only the particles at the surface have enough energy to change from liquid to gas. Hence, evaporation is a slower process than boiling even though it achieves the same state change. Both are types of vaporization. The opposite of this vaporization process is condensation, transition from gas to liquid. Think of a cold can of soda on a hot day, those water droplets on the outside, or the dew on the grass in the morning, or the steamed up mirror after a hot bath. Even the clouds in the sky or a foggy windscreen on a car. These are all examples of condensation. Water vapor in the air has cooled down to form liquid droplets of water. Transition between solid and liquid, so melting and freezing. Think of the Arctic sea ice. In the summer, when air temperatures are warmer, more heat energy is absorbed by the ice. This causes bonds to break between the ice-water molecules and the ice starts to melt. The solid ice becomes liquid water, but in the winter, the air temperatures are colder and so seawater freezes and the ice starts to form again. There is less heat energy within the ice, and so more bands can form, holding it together as solid ice. Did you know that sometimes when solids are heated, they can turn straight into gases? This is called sublimation. This is only demonstrated by particular materials such as solid carbon dioxide. When subjected to a certain pressure, it will turn straight into gaseous carbon dioxide. Liquid carbon dioxide does exist, but it only occurs under very high pressures. Similarly, gases can turn straight into solids when cooled. This is called deposition.
All organisms require energy for their growth and development. Lack of ecological understanding leads to the overexploitation of energy resources such as light, nutrition, and radiation, leading to its depletion. Proper knowledge of ecological requirement prevents the unnecessary wastage of energy resources, thereby conserving energy for future purposes.
An element is a pure substance. In other words, an element cannot be broken down into a simpler substance by physical or chemical means. An element is made up of only one type of atom. An atom consists of a proton, neutron, and an electron. Some common examples of an element would be carbon, oxygen, or iron. The elements are arranged in the periodic table based on their number of protons. For example, sodium has 11 protons, potassium has 19. The number of protons of elements always stays the same. Each element has its own unique set of properties.
Atoms are the basic unit of chemical elements. They contain subatomic particles in their nucleus and in the electron cloud that surrounds the nucleus. These subatomic particles are protons and neutrons that is located in the nucleus and electrons located in the cloud or field that surrounds nucleus. Protons have a positive charge, neutrons are uncharged, and electrons have a negative charge. The number of protons and electrons are equal, so atoms are electrically neutral particles.
When you look at the periodic table, you will see that each element has its own box, and within their box you'll find two numbers. The atomic number operates on number and the mass number. The atomic number has a symbol set. This number tells you how many protons are in one atom of an element. The number is always the same for all atoms of a particular element. Atoms of different elements have a different atomic number, meaning they have a different number of protons. For example, an atom of hydrogen has an atomic number of 1 because it has 1 proton, but an atom of oxygen has an atomic number of 8 because it has 8 protons. Next is the mass number. It has a symbol A. The mass number tells you how many protons and neutrons are in one atom of an element. We need to remember that protons and neutrons has relative mass of, and that electrons are so small that their mass does not need to be considered in the mass number of an atom. So if we know the mass number of an element and we know the atomic number, we can calculate the number of neutrons in an atom of particular element. Atoms of the same element with different mass number are known as isotopes. It is an atoms of an element which have the same number of protons but a different number of neutrons. If we look at carbon and nitrogen, they have different mass number but they also have different number of protons. Therefore, they are not isotopes. They are completely different elements. Different isotopes of elements do not have separate positions on the periodic table. They occupy the same spot because they have the same number of protons. When an atom gains or loses electrons, they develop a charge. Electrons are negatively charged, so the gain or loss of electrons will create a charge. These charged particles are called ions. When an atom loses electrons, they become positively charged. Positively charged ions are called cations. When an atom gains electrons, they become negatively charged. Negatively charged ions are called anions. Each scales measure how acidic or how basic a substance is. It ranges from 0 to 14, with 7 being neutral. When a substance has a pH of 7, like water does, it releases an equal concentration of hydrogen and hydroxide ions. When a substance has a pH of greater than 7, it is classified as a base and releases a greater concentration of hydroxide ion. The more hydroxide ions that are released, the more basic the substance is. Bases tend to feel slippery and often used as a household cleaners. Milk of magnesium and ammonia are both common bases. When a substance has a pH of less than 7, it is classified as an acid and releases a greater concentration of hydrogen ion. The more hydrogen ions that are released, the more acidic the substance is. Acid tend to taste sour. Lemon juice, stomach acid, and coffee are all examples of acid. Many of the compounds found in living things contain the element carbon, which is usually combined with other elements. This large class of chemical compounds in which one or more atoms of carbon are covalently linked to atoms or other elements, and most of the times it is hydrogen, oxygen, or nitrogen, are called organic compounds. There are several important groups of organic compounds found in living things. They are proteins, carbohydrates like sugar, lipids, which are fat and waxes, and nucleic acids such as DNA and RNA. Organic compounds can be very large and complex. A compound that does not contain carbon and is usually simple. Every living organism is made up of cells, from plants, the lowliest worm, to the most complex human being. Cell is a small self-contained unit within a whole organism, kind of like a room within a house. It is the smallest unit that can be classified as a living thing. We can think of them as the building blocks of life. Enzymes are really important proteins that speed up the rate of reaction in photosynthesis, respiration, and protein synthesis. It is known as biological catalysts because they lower the activation energy of the reaction. Hence, they are unchanged at the end of the reaction and can be reused. Some enzymes help to break down large molecules into smaller ones. Others build up large molecules from small ones, and some enzymes help change one molecule into another. Whether we are eating ice cream, lying still, or running a marathon, chemical reactions are taking place inside our body. All of the chemical reactions that takes place in the human body are called metabolism. There are two types of metabolic activity going on inside human body. When large molecules are broken down into smaller molecules for energy, it is called catabolic reaction. After eating ice cream, the sugar and ice cream can be broken down into simpler forms that can be used to produce chemical energy in the body called ATP. Small molecules can be combined into larger molecules in order to store the energy. The chemical reactions in the human body that combine small molecules into larger molecules are called anabolic reactions.
Now, let's proceed to the concepts of ecology relating to energy, living organisms, ecosystems, and trophic levels.
The ability or the capacity to do work is called energy. The food that we eat gives us energy to do various activities. Types of energy includes mechanical, thermal, nuclear, chemical, electromagnetic, sonic, gravitational, kinetic, potential, and ionization. But for now, we will focus on mechanical energy, which is the kinetic and potential energy, along with the chemical and heat energy. Because a bowling ball is moving, it possesses a type of energy called kinetic energy. Kinetic energy depends on two things. First, kinetic energy depends on the mass of an object and also the velocity of an object. For example, we have the bowling ball and the golf ball rolling on the same lane with the same velocity. The bowling ball has more mass than golf ball. That means it has more kinetic energy. The bowling ball most likely knocked down more pin. Potential energy. Just like an object held at height, a compressed spring and a stretched rubber band has potential energy. All these objects are storing energy in them, waiting to be released. That's why it's called potential energy, because these objects have the potential of doing work. Chemical energy. Chemical energy is the energy stored in a substance or materials. For example, we have lighted candle. This contains chemical. Solid fuels have stored chemical energy. That stored chemical energy is found on the foods that animals and humans eat, the digested foods and the oxygen on the body combined. Also medicines, because it contains chemical substances. We need to remember that chemical energy is released when a chemical reaction takes place. The energy is either released or absorbed during a chemical reaction. Heat energy. Heat is the transfer of energy from objects of different temperatures. As objects warm up or cool down, their kinetic energy changes. Heat energy flows from a warmer object to a cooler object. We all know that it includes the method of conduction, convection, and radiation. Conduction involves the direct contact between objects and usually occurs among solids. Convection is caused by unequal heating, and the density of the different objects causes movement of fluid away from the heat source. And lastly, the radiation. It occurs without objects touching and occurs in space.
Units of energy. 1 joule is the work done when 1 kilogram is accelerated to 1 meter per second. 1 calorie is the amount of energy needed to heat 1 gram of pure water. 1 degree Celsius. Noted that 1 calorie is equivalent to 4.184 joules.
Thermodynamics. According to scientists, thermodynamics and its laws are the tools which govern the fate of the universe, and they also added that thermodynamics is a combination of two Greek words, therme, which means heat, and dynamics, which means motion. Therefore, thermodynamics means motion of heat. It is a branch of science which deals with relations among heat energy and work done by the heat energy. First law of thermodynamics. The first law of thermodynamics says that heat is a form of energy, and as what all other forms of energy are subject to, it follows the law of conservation of energy. So what does this mean? It means that heat energy also cannot be created nor destroyed, and can only be transferred to one form or another. This law is about heat as energy and follows the law of conservation of energy. This law is a reversible process. Second law of thermodynamics. Second law of thermodynamics states that heat transfer occurs spontaneously from higher to lower temperature bodies, but never spontaneously in the reverse direction. This means it is a reversible process. Let's call this as high to low.
For any process, a natural flow will always be from higher energy value to lower energy value. For example, coffee. The temperature of coffee is higher than its cup, and as what it says, from higher energy value. So the temperature of coffee gets transferred to the cup, which is cooler, lower energy value, and that's why the cup gets hotter. Or try a compressed gas in a balloon. If you open a small hole in a balloon, does the outside air enters the balloon? No. Instead, the gas in the balloon goes outside, transfer its pressure to the outside air, because the gas in the balloon has higher pressure than the outside air. Energy for life. At or near the surface of our planet, all life is powered by the sun in a process called photosynthesis. Plants capture light energy and store it in chemical bonds. Then animals eat those plants, so at the bottom of any food chain, you'll find photosynthetic organisms. But what about deep underwater where there is no light or sunless ecosystem? How can life survive? The answer is chemosynthesis. Chemosynthesis isn't actually that different from photosynthesis, but instead of light energy powering life, chemical energy powers it. Methane and sulfides that bubble up through the Earth's crust are used by chemosynthetic bacteria that release energy which powers a process similar to photosynthesis. Organisms that then either eat the bacteria or provide a home for them within their tissue, and then use the energy that the bacteria produce. These two worms, for example, have no mouth and no gut. They don't eat like most animals do. Instead, they depend entirely on chemosynthetic bacteria to survive. So there are two parallel food chains on this planet. One gets its energy from the sun, and another gets its energy from molecules that seep out of the Earth's crust. Solar energy is essential for life. There are two reasons why. First, the sun provides warmth. Above 40 degrees Celsius, most biomolecules begin to break down or become distorted and non-functional. Biomolecules include carbohydrates, lipids, nucleic acids, and protein. When biomolecules begins to break down into the respective amino acids, it will then transform into protein that will help our body to function properly and regulate growth. At low temperatures, some chemical reactions of metabolism occur too slowly to enable organisms to grow and reproduce. And second is, almost all organisms on the Earth's surface depend on solar radiation for life-sustaining energy. Photosynthesis converts radiant energy into high-quality chemical energy in the bonds that hold together organic molecules. Producers which use photosynthesis to create their energy are a large source of energy in an ecosystem. Plants and algae are examples of producers. As consumers eat these producers, carbon bands are broken and energy is released, and this energy is transferred from one level to another. From species to ecosystem. Ecology. The word ecology literally translates to the study of home, our home planet Earth. The more specific definition of ecology is the study of the relations of organisms to one another and to their physical environment. It answers questions like, how do living things interact or rely on each other, or on their surroundings? The largest ecological system we know is the biosphere, planet Earth. All life on Earth is in the biosphere. If you zoom into one ecosystem, it is little easier to see all parts working together. An ecosystem is all the organisms and non-living environment found in a particular place. The living things in this found ecosystem includes fish, turtles, aquatic plants, algae, insects, birds, and bacteria or organisms interact in ways that affect their survival. For instance, fish and insects eat aquatic plants, and the turtles eat the fish. This environment is called biotic factors. While the non-living or physical and chemical things, which includes the chemical composition of the pond, its pH, its levels of dissolved oxygen and carbon dioxide, and its supply of nitrogen is called abiotic factors. A biological community is all of the interacting organisms in an area. It does not include the non-living factors. A population is all of the organisms of one type of a species in the area, whereas the species are the group of organisms that are genetically similar. And the organism refers to an individual animal. Productivity. Productivity is the rate of biomass production. It is an output. But who do you think is responsible for the production in an ecosystem? The producers, right? Because the producers is the only one who can actually produce something without anybody's help. Consumers and decomposers are all dependent on the producers. Biomass is the matter which is being produced out of life. How much amount of food is being prepared by the producers of the ecosystem? Because all other organisms is dependent on the producers. So the producers should have really high productivity. There are two types of productivity. The first is the primary productivity, which is the amount of biomass produced during ecosystem. The major bulk of biomass is being produced by the plants. Next is the secondary productivity, which is the amount of no biomass produced by consumers. They are the organism who eats the plant. A given ecosystem may have very high total productivity, but if decomposers decompose organic material as rapidly as it is formed, the net primary productivity will be low. Food chain, food web, and trophic level. Matter and energy passes from one organism to other, connecting living things like links in a chain, called food chain. This series of organisms at various biotic levels form as a food chain. Each level or step of the food chain forms as a trophic level, and there are 4 trophic levels: the producer, primary consumers, secondary consumers, and tertiary consumers. All of the energy in Earth's food chain comes from the sun. Plants capture some of it and convert it into food through photosynthesis. Because plants make and produce their own food, they are called the producers. A food chain begins with a producer. Example is grass. That's because animals cannot create their own food. They must eat or consume energy from the other sources. That's why animals are called consumers. The second link in a food chain is a consumer that eats plants, herbivores, which is called primary consumers. Example of this is a grasshopper. When they eat plants, some of the energy the plant captured from the sun is transferred into the animal's body, where it is used for things like moving, breathing, and growing. Next comes is the secondary consumers. This consumer is a carnivore and gets their energy by eating other animals. An example of this is a frog. When the frog eats the grasshopper, part of the energy that the grasshopper got from the plants is transferred to the frog. Scavengers are included as the second consumers on a food chain, but they contribute to decomposition. Scavengers are animals that consume dead organisms that have died from causes other than predation. Back to the food chain, the frog gets eaten by a tertiary or third level consumer, which is a snake. The snake is eaten in turn by a hawk. The hawk is the apex predator and the quaternary or final consumer in this food chain. Apex predators are not hunted and eaten by any animals. Just because they don't get eaten doesn't mean that they don't contribute to the food chain. When an animal dies, their body is broken down by decomposers. Detritivores or detrivores and decomposers are the final part of food chains. Detritivores are a type of decomposer. It differs from decomposers in that they consume material to break it down. Decomposers are usually bacteria and fungi that break down dead plants and animals into nutrients in soil that in turn help the plants at the beginning of the food chain to grow. Natural ecosystems usually have more complicated food chains. A network of interconnected food chains is called a food web. The arrows used to show which direction the energy flows and help keep track of the connections between organisms.
Ecological pyramids. ecological pyramid is another way to show how energy flows through an ecosystem. An ecological pyramid is a diagram that can show the relative amounts of energy, biomass, or the number of organisms at each trophic level in an ecosystem. Let's look at 3 types. First pyramid is the pyramid of energy. In this pyramid, each level represents the amount of energy that is available to that trophic level. Each time you step up in a trophic level, there is an energy loss of 90%. Next, pyramid of biomass. In this pyramid, each level represents the amount of biomass consumed by the level above it. Finally, the pyramid of numbers. Each level represents the number of individual organisms consumed by the level above it. So, there we go, 3 types of ecological pyramids, which is one way to show how energy flows through an ecosystem. Material cycles is the maintenance of these conditions which requires constant recycling of materials between biotic or living things such as plants and abiotic or non-living things such as soil of our ecosystem. Water cycle is the most familiar cycle and it explains the path of water through environment. Let's start the cycle with the evaporation of water. When the sun heats up the rivers and oceans, water becomes water vapor and it rises up into the air to form clouds. When water vapor reaches up in the sky, it turns into tiny droplets of water. This is known as condensation. This moisture in the atmosphere may be transported around the globe until it returns to the surface as precipitation. Precipitation may take the form of rain, snow, sleet, or hail. Now, once this water reaches the ground, 1 or 2 processes may occur. Some of the water may evaporate back into the atmosphere, or water may penetrate to the surface and become groundwater. The groundwater may take several different paths. The groundwater may seep in its way into the oceans, rivers, or streams. Or it may go into an aquifer, which is a body of saturated rock through which water can easily move, or it may be released back into the atmosphere through transpiration. Transpiration occurs when leaves from trees and other vegetation give off water vapor through pores in their leaves. Some water on the Earth's surface is not absorbed by the plants or become groundwater, and it becomes surface runoff. This runoff may empty into lakes, rivers, and streams, and then is carried back to the ocean where the cycle may begin.
Carbon cycle is an element that's crucial to every living organism. It is also a key component of our atmosphere. Carbon cycles through our Earth, the ocean, biotic factors, abiotic factors, and the air constantly. The carbon recycles among 5 major locations or influences. These major items include atmosphere, the terrestrial biosphere, the Earth's interior, the ocean, and human influence. Let's take a look at what happens at each of these items' areas or influences. Carbon is found in the atmosphere in at least 2 forms, carbon dioxide and methane. This atmospheric carbon can be absorbed by autotrophs, like plants and plankton, to be used by photosynthesis. It can also be absorbed by bodies of water and the oceans. When carbon is absorbed by the ocean, it reacts with the water and creates carbonic acid. The terrestrial biosphere is another term for the Earth's land. There are several paths carbon can take on the biosphere. First, there is an exchange between plants and animals. Plants absorb carbon for photosynthesis, and animals release carbon during cellular respiration. Also, heterotrophs eat plants that contain carbon. Animals also release carbon as methane during digestion, and the soil contains decomposers that release carbon into the atmosphere and the soil. Carbon is also stored in the Earth's interior. Carbon in the lithosphere includes fossil fuels like coal, oil, and natural gas,
Shale and deposits like limestone volcanoes may release some of this carbon stored in the lithosphere. The ocean has the greatest exchange quantity of cycled carbon and stores a large amount of carbon. The ocean absorbs carbon in the form of carbon dioxide. The ocean also has a large amount of plankton that absorb carbon dioxide for photosynthesis. Humans also influence the movement of carbon. Humans burn fossil fuel which releases carbon into the atmosphere. Also, the production of clinker, which is used for cement from limestone, also releases carbon into the atmosphere.
Nitrogen cycle. Our atmosphere is made up of 7 to 8% nitrogen. We need the nitrogen for our DNA and for proteins. We just can't breathe the nitrogen like oxygen, but we must absorb nitrogen in our food. Nitrogen follows a cycle where it travels from the atmosphere to the soil, to animals, and back in a cycle. Nitrogen in the atmosphere falls to the earth by precipitation, such as rain or snow. Once in the soil, it finds its way to bacteria on the roots of plants. At the roots, the nitrogen is combined with the hydrogen to make ammonia in a process called nitrogen fixation. Lightning in the atmosphere can also do this. Now, ammonia is toxic, so additional bacteria combines this ammonia with oxygen in a process called nitrification. At this point, the nitrogen is in cyano form called nitrite. Additional nitrifying bacteria convert this nitrite to nitrate. At this point, plants can absorb this nitrogen in a process called assimilation. However, not all of the nitrate is absorbed, but some of it goes to the bacteria that release the nitrogen to the atmosphere in a process called denitrifying or denitrification. The nitrogen returns to the atmosphere. Also, once this animal after it eats the plant, the animal either dies or need to get rid of waste. Another type of bacteria then takes this and along with decomposers and breaks this nitrogen either in the waste or dead animal and by process called ammonification. The nitrogen can enter the cycle once again at nitrification and the cycle continues. I hope that helps with the nitrogen cycle, which is how nitrogen keeps recycling itself.
Phosphorus cycle. Along with the water cycle, the carbon cycle, the nitrogen cycle, the phosphorus cycle is another biogeochemical cycle that is essential for life on Earth. A biogeochemical cycle is a pathway by which a chemical substance moves through biotic and abiotic compartments of Earth. Although phosphorus is not found on the atmosphere, it still plays a very important role in plants and animals on Earth. Phosphorus is essential for plant and animal growth as well as the health of microbes inhabiting the soil. Phosphorus is very important for the production of DNA and RNA that helps to make up cell membrane and the production of ATP. The phosphorus cycle is a slow process and involves 4 key steps. Step 1. Weathering. Phosphorus is found in rocks. Weathering along with rocks breaks down the phosphorus and travels to the soil and in the water sources. Step 2 is absorption by plants and animals. Once in the soil, plants, fungi, and microorganisms are able to absorb phosphorus and then grow. Some of it also makes its way to the ocean and fresh water, and animals are able to drink this water and absorb the phosphorus. Plants absorb the water along with the phosphorus, and then the animals eat the plants while the phosphorus moves into the animal in this way also. Step 3. Returning to the environment by decomposition. Animal excrete waste and decomposers are able to use the phosphorus in the waste material. Furthermore, when the plants and animals die, the bacteria convert the organic phosphorus into inorganic phosphorus in a process called mineralization. And then, step 4. sediment to rocks. Some of the phosphorus gets buried in settlement, which over time become rocks, and the cycle continues. Some of the phosphorus in the soil gets washed to the ocean, where similar process takes place. Plants and animals in the ocean absorb the phosphorus, die, and decompose, and some of the phosphorus ends up as sediments in rocks. Humans have had a significant impact on the phosphorus cycle. Fertilizers containing phosphorus is added to the soil. This helps the plant grow. However, when the levels of phosphorus are too high, the overabundance of plant nutrients serves and drives excessive growth of algae. When these algae die, they can be toxic to the plants and animals in the ecosystem.
Thank you for listening. God bless.